Good morning, my dear young friends. Today I am going to discuss one of the important concept of acid-base catalysis, that is the Bronsted catalysis law. You may aware of details of acid-base catalysis, and you know the exact definition of specific acid-base catalysis as well as the general acid-base catalysis. So on the basis of this acid-base catalysis, Jane Bronsted, you all know, is a well-known chemist. He actually derived two important laws, and which is very important in the context of acid-base catalysis. So today I am going to discuss very briefly the Bronsted catalysis law. Now, if you see the literature, there are a large number of applications are available for the Bronsted acid as well as base catalysis law. Sometimes it may be regarded as Bronsted relation. You can call it Bronsted relation, or you can call it, sometimes it is Bronsted catalysis law. Now, if you want to learn much about this Bronsted catalysis law, there are large number of research paper available. Even you can refer the original research paper of the Bronsted and Pedersen. But I am showing here one of the most important review articles. So you can understand the importance of that work. Although it is a very old research paper, in fact it is a chemical society review. And a very well-known physical organic chemist, Professor A.G. Kresge, he actually written this paper, the Bronsted relation, recent developments. Now, before I start this important law, actually there is two laws. And in one sentence, if you ask me, sir, what is actually Bronsted catalysis law? It is nothing. It is the relationship between catalytic constant and the acid strength of acid and base. Suppose you are performing one experiment. Acetone iodine reaction in the presence of acid as well as some general acid. Or you are performing some experiment, I will show you the example, vinyl or ethyl vinyl ether in the presence of strong acid as well as the general acid. Suppose you are using acetic acid, you are using formic acid, you are using chloroacetic acid, nitroacetic acid, methyl acetic acid. That means you are changing the reagent. Now, when you observe the result, there is a change in the rate constant. And with the help of this Bronsted catalysis law, you can figure out that what type of mechanism is like that. So there are two actually important. One is for acid strength and the catalytic activity in general acid catalysis, and another is base strength and catalytic activity of general base. So there are two forms of Bronsted catalysis law. I will show you that form. It is very simple. Now the general form of the, you can sit anywhere like that. If there is a focus is all right, then you can sit there. So the general rule is that it is actually catalytic constant, okay, and it is actually acid dissociation constant. It is one constant and it is alpha. So if I take the logarithm, so what I should get, log of k for general acid catalysis reaction. Now this alpha, you come here, and this G can be, I can write like, I can write this constant is suppose G. Similarly, if it is general base catalysis type of the reaction, then in place of general acid reaction, I am using general base type of the reaction, and the slope value here is alpha, here is beta 4. So the reaction is exactly same. Either you will get the alpha value or beta value, and I will show you the range of this alpha value and beta value. So when you plot a graph between that rate constant of general acid catalysis reaction and general base catalysis reaction with respect to that log K or pK, so you will get the slope value alpha or beta. So on the basis the magnitude of that alpha beta, you can throw some light about the reaction mechanism. So it is very simple. I will show one or two examples. Now this relation is actually derived from the consideration of the free energy relationship, and if you have not forget that during your first semester, or I think in second semester, I had told you one very important reaction, that is the, I think, saponification of ethyl benzoate and pK of the benzoic acid. Substituted benzoic acid, para-nitrobenzoic acid, para-chlorobenzoic acid, para-methyl, para-methoxy, and you determine their ionization constant or pK in one hand. Another hand, you determine the rate constant of that ethyl benzoate reaction with sodium hydroxide. Fortunately, when you plot a graph between that log K of second order rate constant pK, there is a straight line. That means there must be some relationship between the free energy, because you all know that delta G is equal to minus RT log of K, equilibrium constant. And if you understand the transition state theory, there is a free energy of activation. So this is also a correlation. This Bronsted catalysis law is also a linear free energy correlation. So therefore, always we should consider that free energy. And if you ask me, sir, what is the range of that alpha and beta, it is in between 0 and 1. Similarly, beta also normal range is sometimes 1 or 0. So then you can figure out the reaction mechanism. Now, this is a very important point. You must see very carefully that the role of reagent. I will show you the example. And the correlation analysis to reaction series with a given substrate in various reagents. Because you know that if you are using acetic acid, the pK of acetic acid is 4.76 at room temperature. You replace the acetic acid and you will use the formic acid. The pK is different, 3.57 or whatever it is. So naturally the strength of reagent will different. Suppose you are using para-methoxy or not para-methoxy benzoic acid, pK is different. So therefore it is called the role of reagent. So when you plot a graph between log of K versus log of K or pK for a series of related acid, gives a linear plot, and with the help of that slope value you can predict the mechanism. I will show you one example and then it is very simple. This is a very common example of Bronsted catalysis law, and it is available most of the standard textbook of physical organic chemistry. That is the hydrolysis of ethyl vinyl ether, or you can use the reaction of acetone and iodine type of the reactions. So you see, this is the our reagent. This is our reactant C2H5OCH2. It is ethyl vinyl ether, and temperature is 25 degrees centigrade, and a general acid is here. This H can be acetic acid, formic acid, chloroacetic acid, methyl acetic acid, or nitroacetic acid, and hydrogen ion is also there, and the product is alcohol and acetaldehyde. So I am just giving this example for general acid. For general base, I can use the nitramide. Second example. So I'll show you the example. I will get different rate constant. Then I plot a graph between that rate constant observed by the experiment, and these are the standard pK value of this substituted acetic acid. So there will be a straight line, and if there is a straight line, and if we follow the Bronsted catalysis law, I will get the alpha or beta value, then I can predict the mechanism. Now I am showing you for general base catalysis reaction. So decomposition of nitramide. So of course, in the presence of a general base. So one example is general acid, this example is general base. Now see very carefully this I have taken this values, it should be point. So first I am taking all these values. It is, if you can see any organic chemistry book, Jerry March or any other books, you will get because this is a standard value. So for example, I can start with acetic acid 4.76 pK. Naturally, then formic acid strength is different, 3.75. Chloroacetic acid, you all know, plus I effect, minus I effect, you all know all these things. I will not discuss all these things. So chloroacetic acid is 2.87. Then propionic acid, methyl acetic acid is 4.88. So at least for a graph, we need 4 or 5 points in order to get good plots, 4 or 5. So some are electron withdrawing, some are electron donating types of the group. So this is the standard value. Now I am using that same reaction. Again I am showing you that reaction, this reaction. So in H, different acid, second order rate constant. So suppose it is you can imagine, this may not be correct value, but I am taking from a very good book, The Physical Basis of the Organic Chemistry by Howard Maskell, Oxford University Press. But actually these data, I think they have collected from Journal of American Chemical Society 1971, that crazy. So I am unable to retrieve that original research paper from where they are getting that. But just in a nutshell, what the rate constant of acetic acid. In the presence of acetic acid, ethyl vinyl ketone is suppose 0.00138, suppose, and formic acid it is 0.00672 in. Now it is chloroacetic acid where pK is, you know, that 2.7387, naturally stronger than this acetic acid, and you know that trichloroacetic acid or dichloroacetic acid is acidity 1.2. I am not going to that point, but here you also suppose 0.034. Then I take this propionic acid where it is also less than this, because you saw the pK. So that means there must be a, now you can understand, there must be a correlation between that pK and the rate constant. If the pK is 4.88, which is higher than acetic acid, rate is decreasing. Whereas cyanoacetic acid pK is 2.47, that is, it is stronger than that chloro. So I am getting 0.0442. So if I just plot a graph, if I ethyl, vinyl, ether. So our objective is, you know, that K is equal to, suppose, Kc alpha G, like that, or whatever it is. So natural log of K alpha natural log of Kc plus natural log of G, or whatever it is. So that, if I am using, this is actually Bronsted plot. So log of Kc or Ka and Pk, 2, 3, 4, like that. The last is 4.88 or 5, suppose. Our range is 2.8 to 2.5. I am using from acetic acid, chloro, or if I take the log -1, -2, -3, like that. -3, like that. So it is one type of linear free energy relationship, because in this chapter you will see that most of there is a possibility of different types of question. That is the Hammett equation, linear free energy relationship, even in Bronsted catalysis law. You should be very careful. There is a possibility to ask the numerical problem. So suppose this is the different substituents, maybe 4 or 5. Maybe some scattering is also possible. And this alpha value is equal to 0.7. If you solve this problem, you'll get. So whether the proton transfer is, or the transition state is very similar to that reactant or not. Now the last part is the derivation. How do you derive this equation? So I'll show you in 5 minutes. So it is a very simple. Let me summarize that. I am just showing you 2 examples. One is Bronsted catalysis law for general acid catalysis reaction, and the Bronsted is a short question, so short type of the question. What is Bronsted catalysis law? What is the application of the Bronsted catalysis, or some numerical problem? So there are many numerical problems available in the books. I am using only one, taking from the books of the Howard Maskell, ethyl vinyl ether, and this plot is based on the data which I have shown you previously. So if you plot this curve, so you will get a positive alpha value. So this is called the application of the Bronsted catalysis law. Now how we derive these things? Only 2 minutes derivation. Now let me first do it for the general, let me first do it for the specific acid catalysis reaction. Suppose there is a S and H. You all know all these things, because so and then SH is equal to product, whatever it is. So you know that rate is equal to some, suppose K, K2 you can write. Here you can write K1 like this. So K2 SH. And in normal cases, when we perform the experiment, rate should be K1, or you can call it a rate constant. It depends upon the S as well as it depends upon the. Now, if we substitute the value of K, equilibrium constant, SH, S, and H. So, if I substitute the value of SH here, so I will get K2, capital K, S, and H. So if I compare this one, rate is equal to K1 SH, so K1, so I will get K1, or it is actually sometimes I can get K, it is equal to K2 and K, which is, so what does it mean? That there is a relationship between this catalytic constant, it is catalytic constant, or observed rate constant with that K of that species. So it is a thumb rule for specific acid-base catalysis. So it is specific acid. Now the last derivation is for general acid catalysis reaction using the Bronsted catalysis law. Let me solve it. Clean all. So the last derivation for, I'll show only one, Bronsted catalysis law. So there are three species, because suppose HS, our species, I need one HA, and third is hydrogen ion. I can give one example, like suppose I am using CH3 COCH3 ketone reaction, acetone. First it is hydrogen. So there is a protonation form, CH3 COH, CH3. It is another example, hydrogenation of acetone, that CH3 COH, CH3. That A means that general acid part. So it will give you CH3 COH, CH2 plus H. So I am showing the another example of Bronsted catalysis law. Before that, I used that ethyl vinyl ether. So now I am deriving it. Very small derivation. So let me use that substrate why I have written H, Because red color, because this proton is to differentiate between that proton and the proton coming from that hydrogen. So therefore I just italics H plus this hydrogen. You know why I have given the red color or slightly italics, to differentiate between the proton of this species and proton from that H3O species. So therefore I have created italics here. So again, H S you can call it. Only two steps. This is the first step. Second is H S H react with general acid, suppose it is. You can call it name whatever it is. So it will give HS plus H. So because here actually main that A is maintained with the help of a buffer you know, general acid. So our rate maybe depends upon this species as well as this HA, acetic acid, propionic acid, formic acid, chloroacetic acid, whatever this is. So I can call it is a rate. Sometimes it depends upon the Ka, I can write it depends upon the HS is definitely species, and it also depends upon the H. Any second thing. But here actually rate, this is slow step, this is fast step. So you know that rate determining step, I can, if I write it is a K1 or K2, whatever it is. So you can write K2. H, some tilted H, S plus H. Very simple. And isn't it? Just to remember that first derivation using this general specific acid base catalysis reaction. I have to remove this part, the red color. Just it. So last step, I have to remove these things from here. That means I can write like that K is equal to H S H HS So substitute the value of this HSH. Very simple. So you know that it is actually K of this HS. These are, if you see some good books like John Sauter correlation analysis or Craig G's correlation analysis, you will get all such type of, or any research paper you will get all these things. But most of the common book you will not find the complete derivation. They just give the different types of organic reaction using the Bronsted catalysis law. But this is the course of the physical chemistry. So therefore, I am trying to show you the genesis of that Bronsted catalysis law. Okay, so I am just giving the acid base concept part. So you just write here rate is equal to K2. Very simple. This whole unit is simple. Capital K, so in place of HS, and H plus and A negative. Now the last part is that, so I am getting three things, as because you know that I have already shown you that different types of pK values of acetic acid, formic acid, cyanoacetic acid, anything. So I have to consider that these, whatever these general acid, weak acid, acetic acid or whatever it is, so it gives actually plus A negative. So this K is different. It is the protonation constant. But this K here, you can substitute, you can write A. This is actually acid strength or base strength of the different substituted acids you are using. So therefore, just to differentiate between this capital K and K subscript A is and HA. So I can write that A negative is equal to Ka Ha divided by hydrogen. So last step, you just substitute the values of A. Substitute the value of A, you know. So this hydrogen, so what I am getting, K2 green color, K and Ka, you see Ka, or I can use the red color because this is the most important part. And of course this HS and HA. And as I told you here, I have written here that it is actually depends upon these things. So if I compare this rate and this rate, so I will get final equation. I will get Ka. K is equal to this K2K, can be Z or constant, and Ka. So what I am getting, so that is, if I write Ka is the catalytic constant, observed rate constant of vinyl, ethyl vinyl ketone or ethyl vinyl ether or acetone or whatever it is, and this is, suppose this is a constant Z and this is Ka, acid strength of this thing. So if I take the logarithm of this thing and if I plot a graph with that, there is a relationship between this and this. So then if we plot a graph between very simple. So K alpha or KB G beta, like that. So this is actually empirical relationship called Bronsted catalysis. So similarly, if I take for base, B plus H2. B plus OH negative. So here that place of B we will write. Okay. So this is now let me summarize the whole thing, that it is one of the example of general acid and general base catalysis reaction, and Bronsted and Pedersen actually they discovered this very simple but very important in organic chemistry, that there must be a relationship between the catalytic rate constant and the acid or base strength, and ultimately it is one of the example of linear free energy relationship. Ultimately the free energy plays a very significant role. So just remove it, and I think you will understand this general basic catalysis. So thank you very much. Oh, thank you.